Hello everyone, welcome to the third session of electromagnetic theory and interference. In this session, we will be seeing about Cartesian coordinate system. Before seeing that, let us understand what is coordinate system and why it is required in electromagnetic theory. So we know that in electromagnetics, the physical quantities that we are studying are the function of both space and time. So we have to define all points uniquely in space. For that, we require appropriate coordinate system. An orthogonal system is one in which the coordinate surfaces are mutually perpendicular to each other. So we are going to discuss such an orthogonal system. This used in practical applications. So Cartesian coordinate system is the first one that we are going to see in this session. In the second module, we will discuss about circular, cylindrical, and then spherical coordinates. And we will consider the transformation between all these coordinate systems. So how we choose a particular coordinate system, it depends on the problem statement that is given. It best fit that problem statement. So let us see about the Cartesian coordinate system. The coordinate variables are x, y, and z. So these are the coordinates: x-axis, y-axis, and z-axis. All are placed mutually perpendicular to each other, and these are the limits. So it ranges from minus infinity to plus infinity. Suppose I have defined a point P here. So here all the coordinates are having the positive values. Whereas if I see here, since it is along the negative y-axis, so the value for the y position is -2. How to let us understand in each coordinate system, we are going to see how to write a vector, unit vector, then how dot product, cross product is happening between the unit vectors, what is the differential length, differential surface area, and differential volume. These are the outline of this presentation. So we already know how to write the vector in Cartesian coordinate. So we have to take the component of a along the x-axis and multiply with the unit vector ax cap plus component of y vector, that is ay, into ay vector, plus component along the z-axis, that is az into az cap. How to find the magnitude? It is nothing but the root of the sum of the squares of each of the component along each axis. So to define a unit vector along the a vector, I am writing a capital A cap. It is equal to the vector divided by its magnitude. The vector is defined here, magnitude we have found here. So now let us understand how the dot product and cross product of the vectors, unit vectors are happening. So ax dot ay vector, if suppose I dot product, I have to follow one particular order: ax dot ay vector, ay dot az vector, az dot ax vector. So the dot product, if I reverse it also, it is going to be the same. The answer is 0. We already saw in dot product vector dot product itself, the dot product of same unit vectors is equal to 1, but different unit vectors, it is going to be 0. So if I do cross product of the vectors, so ax or cross ay vector gives me the third remaining unit vector. Similarly, ay cross az gives me ax vector, az cross ax give me ay vector. If I take in the reverse vector cross product, if I take in reverse, I will get a negative sign that only represented here. Now let us see the differential length. Already we consider a point P in this coordinate system. Now I am going to consider the differential length. That is dx is now increased to dx. Y-axis now increased to that y point is increased to dy. Similarly z. So I will get a differential surface area like this, volume like this. For this I can find the differential length, that is equal to dx into ax cap plus dy into ay cap plus dz into az cap. So the differential normal surface area, how can I write? So I have a 3 differential normal surface area. Okay, so along the unit vector ax, I have dy into dz ax cap. This is the differential surface area, length into breadth. Similarly, along the y-axis, dsy vector is equal to dx into dz into ay cap. Similarly, for the z-axis, okay, dy into dx into dy into a z cap.